The last talk before the coffee break. Our next speaker is Ioannis Sgouralis, and I'm not sure whether I pronounce it correctly, but I got approval here. Okay. Yeah, he's working with us on drift correction, one of the problems, and you saw that Paolo was introducing that already. So here we come. And
So yes, hello everyone. I am Ioannis Sgouralis, and I will be giving this afternoon's tutorial. So as you can see, there are several keywords in the title of this talk, but actually I will be focusing mostly on the last part, drift correction. And specifically, I will focus mostly on methods and algorithms that we can apply on real time. So basically imagine that as how we can start thinking and developing algorithms and deploy them on real time, that they will instruct the microscope to correct itself while we are acquiring the images. We have already seen some examples in the previous talk. So basically, what is the main topic that I will be talking about is about how we actually start thinking about putting together the machinery that needs to go into our scripts that make drift correction possible. And I want to start by basically giving you some motivation. So what we see here is something that I believe should be familiar to all of you. Of course, before I explain more, I just want to mention that these are not real images. These are synthetic images. However, when we generated them, we used a very faithful, a very realistic simulator that has been provided by Sergey's group. Now, what we see here is basically, you can see a very regular lattice of atoms. Of course, it contains some imperfections. For example, there are holes, and there are sites that contain more than one atoms, and so on. However, I'm pretty sure what draws the attention of everyone in the room and online at this stage is basically this apparent motion that is observed on our data. And of course, this is completely artifactual. It's completely not coming from the specimen. The specimen that we are imaging is completely static. So what I'm trying to illustrate here is that there are some characteristics of the operation of a microscope that are causing very important artifacts in our images. And the reason of those artifacts is basically something very fundamental, is the very fact that while we are collecting data, we are collecting images, we cannot really control with the accuracy that is needed the position of the probe. So basically, we set up the microscope to collect an image, the microscope does its best, and it gives back an image or a sequence of images that are the best that the microscope can do. As you can see in this case, we aim to image something static, but we take something that is moving. So what I will try to illustrate today is start putting together a framework, a conceptual framework mostly, that we can use to instruct the microscope to sense what is happening on the images it acquires currently and try to correct itself. Ideally, in this case, to reduce the motion, to reduce the drift as much as possible. And before I get to the more technical part and start giving you more technical definitions and solutions and algorithms, I just want to mention from the very beginning that we are going to face three very important challenges. First of all is computational time. So the models that we are going to develop and we are going to deploy and we are going to use, they need to be very fast models, models that can be computed on real time. Why? Because if we deploy very difficult models, very expensive models, and we want to correct the microscope while it is working, we are just going to slow down the experiment, and that's a problem by itself. So having this very severe restriction of very low computational time already tell us that we cannot deploy extremely sophisticated models, extremely large models, and so on. And we are going to see some examples later on of what I mean, models that are relatively small and the computations that are associated with those models, they are very efficient. The second challenge that we typically face when we want to come up with solutions that operate on real time and instruct and correct the operation of the microscope is, of course, that very often we have dynamics. The operation of the microscope is modified, is perturbed dynamically during the experiment. And unfortunately, the dynamics, for example, here, the motion that is causing the drift, are uncharacterized, which means we cannot really rely on historical data, we cannot do precalibration, we cannot do all these tricks that we typically do in machine learning to reduce the computational cost. The third main challenge is that depending on what kind of artifact we want to correct, in this case drift, but depending if we have other imperfections that we want to correct throughout the experiment, unfortunately, we need to be thinking about utilizing signals or feedback from the data that we acquire that are problem specific. And we are going to see how this translates, what type of signals and how we can think about utilizing those signals and computing those signals in the special case of drift correction. So, before I continue, because I want to focus mostly on drift correction, I wanted to give you in the beginning a conceptual introduction of what is causing drift, what is causing the images to appear like they are moving from one frame to the other. And in order to do that, I need to be looking closer to what is actually happening while our image is acquired. And we are going to learn very quickly that there are at least two artifacts that have common origin. And this has to do with the uncontrolled positioning of the probe. So I will start with the first one, which is not very prominent in the images that I have just shown, but it's actually a real problem. It has the same consequence. Let's say, for example, that we want to run a very simple experiment, acquire a very small image, which for the purpose of making a clear illustration, I assume it's going to be very, very small. So in this case, let's say we want to acquire an image that has just 5 columns and 3 rows. Real life experiments, we want to acquire much, much, much bigger images. So how a typical experiment will work? We need to decide in the very beginning how we want to scan across the images, how we want to acquire the pixels. Let's say our scan is actually quite straightforward. We start in the first row, then we switch to the second row, third row, and so on. So what I'm showing here with black points is basically what is the intended, what is the ideal trajectory that we believe the microscope will actually take in order to acquire each one of the frames. And in order to make it super, super, super clear, I'm going to highlight that. I will call this the target trajectory. This is what we want to happen. Now, what is happening in reality, of course, is that the microscope is going to actually follow a slightly different trajectory. Let's call that the actual positioning. So let's say we start the experiment. The first pixel that we acquired happens to have no problems, no errors, no perturbations, so it coincides, target and actual positions. But now let's say, as the experiment goes on, we are making a consistent small error. Every time the probe moves, it's not going to hit exactly its target position, but it's going to accumulate a small error. And for the illustration, just for the illustration here, let's say the error is about 1/10 of a pixel to the left and 1/10 of the pixel to the bottom. Of course, this is terrible error. Real life experiments, the error is much, 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 much smaller. However, real life images are much, 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 much bigger as well. So let's say for the illustration that every time the probe moves to acquire a different pixel in our image is going to accumulate a small error. So as you can see, the second pixel that we acquire, target and actual position, they start deviate. And then the probe moves again to acquire the third pixel. So we accumulate the bigger error and the bigger error and the bigger error. And as we keep going, so we keep acquiring pixels of the image, as you can see, we end up at the end having a quite substantial deviation of what is the target position and the actual position. And here, maybe I oversimplify things by illustrating that by assuming that we have a constant error throughout the experiment. In reality, what is causing this error is not as consistent, is not as controlled as what I'm showing here. But there are environmental factors and very many uncontrolled factors that can affect the position of the probe. So if you want to have a conceptual image in mind, you should be thinking something closer to what I'm showing here, where the probe and the error is following some sort of deterministic pattern on which it is superimposed some sort of random perturbations, random fluctuations. So what is happening? We aim for the black trajectory. However, we end up getting something that is closer to, let's say, the gold trajectory. And this means that every time we acquire a pixel, what we really image is not what is happening on the specimen below the target trajectory, but what is happening on the specimen below the gold trajectory. So as you can see, the data that we actually acquire are probing the specimen in slightly different positions. And this is a serious problem because at the end we are patching together the pixels in a regular pattern, and what we see is very, very difficult to interpret. So what I'm trying to say is that this random misplacement, a consistent misplacement of the probe while it moves to acquire one pixel to the next, is actually causing distortion in the image that we actually get at the end. And why this is a problem? Because what we see at the end is distorted images. The bigger the error we do, the more the distortion. The smaller the error, the smaller the distortion, of course. So this is one artifact that has to do with uncontrolled positioning of the probe position. Now, how we typically solve this problem? Typically, if we suspect that our images are heavily distorted, at the end of the day, we need to follow a certain pipeline, a certain processing scheme, very close to what we call image reconstruction and associated methods. Now, if you have used image reconstruction methods, some of them they are simple, some of them they are more complicated, but what they all tend to have in common is that they tend to be very expensive methods, no matter what they do. So correcting for distortion during real time is actually a very difficult task. Now, let's actually try to move to the second manifestation, to the second type of artifacts that we can see by this by having an uncontrolled positioning of the probe. And in this case, let's say, again, we are trying a typical experiment, where in this case, we are going to collect more than one images. So let's say we have frame 1, 2, 3, and so on. And again, the idea is pretty much the same. We decide on the beginning on how we want to scan each image. The first image is going to be scanned, and at the end of the first image, the probe is going to move on the beginning. Let's say it scans the pixels again in the same order for the second frame. Once the second frame is fully acquired, it's going to move in the third frame, and so on. So now, as I have already explained, what we actually see, each frame is slightly distorted because we have slight error that is accumulated within the acquisition of each frame. But because typically the time interval that we need to wait from the acquisition of one frame until the beginning of the acquisition of the next frame is considerably longer than the time interval between the acquisition of one pixel and its subsequent, what's going to happen is that a considerably much bigger amount of error is going to be accumulated in the probe position. And what is the effect is that the second image that we are going to acquire, is not only distorted, but it's actually significantly shifted relative to the first image. And the errors keep accumulating, so the third frame is going to be also translated considerably and so on. So what I'm describing here is that basically the more errors we accumulate, the different manifestation it's going to have on our data. It's not going to cause distortion, but it's going to cause mostly what we see as drift. What I'm saying drift is basically the probe position is going to be deviating from its target position much more prominently throughout the motion of the end of one frame to the beginning of the other frame. So again, the cause of the problem is the same. We cannot control perfectly the positioning of the probe as it's moving from the end of one frame to the beginning of the other frame. And this is something that we see in the results as drift. And sometimes it can be very prominent, like the example that I showed in the very beginning. Some other times, of course, it can be less prominent, but still quite noticeable, even by eyeballing the data without even running any analysis. Now, the good thing here is that typically when we have drift which means we have images, successive images that are just translated relative to its previous image, the mathematical or the computational methodology that we need to follow, they require basically some type of image registration or variants of image registration. And the good thing is that image registration is a relatively cheap procedure to do, which means that as long as we want to just correct drift throughout while the microscope is operating on real time, actually there is a lot of hope because fundamentally the computations that might be involved are not that dramatic. That's exactly what I want to illustrate today and what I want to focus today. How we can actually utilize sort of image registration techniques, adapt them in the right way, and come up with a mathematical method, a computational method, an algorithmic framework that we can use to correct the operation of the microscope while it is actually working. So what I'm going to do next, now that we have already built some intuition of what is causing the problem and how we can actually try to correct for it, what I'm going to try to do next is try to give you a conceptual framework of what are the main ingredients in our methodology that we need to keep track of. So in some sense, I will try to keep the formalism as minimum as possible, but I will try to highlight only what are the important quantities, what are the important variables that we need to keep in our models, and what might be the possible connection between those variables. So once we build a relatively complete conceptual framework, then I'm going to introduce more formalism and I'm going to get into the mathematical details of how we actually manage to run this model in greater detail. And because I want to be relatively close to what is happening on the microscope, I will try formulating a mathematical model that in the beginning is actually very realistic, very faithful, but eventually we will have to basically simplify it a little bit. So if we want to come up with an algorithmic framework to correct for drift, I'm going to start by formulating a very simple situation. Let's say we run an experiment. We want to acquire a number of images. In this case, I'm just showing very small images for just 3 frames. You can think of course, of much bigger images for much more frames. And let's say this is here the trajectory that we intend to scan, how we intend the probe to go through the pixels, acquire the data, and return back to our frame. Nothing crazy, just the simplest pattern. We acquire the first row, we shift to the second row, then we shift to the second frame, and so on. So, because I want to be a little bit more careful here, I'm going to label its pixels. And let's say my W's, these are my first variables, these are the intensities that we record of each pixel. And as you can see, I'm going to use a double indexing scheme to pinpoint the pixels. On the subscripts, I am basically using the frame index. So all pixels on the first frame, they are subscripted with 1. All pixels on the second frame, they are subscripted with 2, and so on. Now, different pixels within a frame, they are also going to take a unique identifier, and these are going to be the superscripts. And in the beginning, and as you can see here, I'm labeling the pixels within a frame sequentially. According to how they are moving, the probe actually moves and acquires them. So we have pixel 1, 2, 3 in the first row, pixel 4, 5, 6 reversed in the second row. Now, as I have said, the values that are recorded for each pixel, the intensities of each pixel, are going to be contaminated by a little bit of error. And this error is going to be sequential. So, for this way, it might be a much better, for this reason, it might be a much better way to visualize the pixels according to the order that they have been acquired. So what I'm showing right now is basically how the pixels have been acquired in the right order. You can see the pixels of the first frame, they form the first group. The pixels of the second frame, they form the second group, and so on. Now, when we try to correct, if we try to correct for imperfections that are happening during the experiment, of course, we need to know a little bit about how those pixel values, those pixel intensities are created. And what we have seen right before is that what matters for the intensity that we record in each pixel is basically the specimen, but also the actual position of the probe, where actually the probe is sitting relative to the specimen when it acquires the corresponding value. So these are going to be my capital R variables. So each pixel is going to be acquired under a different position. And that's why we have the vertical arrows here. Each pixel has its own probe position. Now, as you can see here, I'm already introducing a little bit of spatial annotation, because the pixel intensities, I am using shaded boxes for the pixel intensities. And what this really signifies is that those values are measurements. So there is nothing uncertain about those quantities. However, the actual probe positions, they are left open. So I'm not using any background on those boxes. And what I really want to highlight here is that there is some missing information here. The actual position that the probe sits is something unknown. It's something very, very different than the measurements. Now, what determines the probe position? The first thing that determines the actual probe position is, of course, the target position, where we intend the probe to sit when it acquires its pixel. And these are going to be my little r variables. This is basically what we instruct the microscope to do. Because I plan my images, I plan to scan my frames in the same order every time, there is no temporal dependence on the target positions. Also, because the target positions is something that we pre-specify in the beginning, these are not uncertain variables. These are not variables from the problem at all. So that's why I'm not using any boxes when I denote them. Okay, target position definitely is something that affects and determines the actual position of the probe, but there is something else. What is this something else? Of course, is the error that I'm going to make. These are my D variables. And basically, what is the actual position? The way that I'm thinking is basically target position plus a little bit of error. This is what I call the error displacement. And the error displacement is the main unknown of the problem. This is uncertain information. This is the quantities that I need somehow to gain access at, so I can subsequently correct. And because I want to instruct the microscope to adapt while it operates, I'm going to introduce a third very important quantity in the formulation, and these are going to be my alpha variables, my A variables, which are going to be the intended corrections. So basically, what's the idea? The actual probe position during the acquisition of each pixel is going to be the sum of three different things. Target position, which I know even before the experiment begins, unknown errors, plus some corrections that I need to basically find a way to compute on real time that are going to counterbalance the error. And how I am planning basically to be able to compute values for the correction is because we can assume, or at least is a relatively safe assumption, to assume that the drift evolves, the errors evolve following some sort of dynamics. Now, the dynamics do not need to be necessarily deterministic, but they need to follow some sort of regular pattern. And what I mean here by dynamics is basically when the probe is not moving at all, we would expect no error. If the probe is moving a lot, like what's happening between the end of one frame and the beginning of the other frame, obviously we would expect the accumulation of much bigger error. And when the probe is moving between two successive pixels, simply because this is a much faster procedure, we would expect the accumulation of much smaller error. So trying to translate those expectations and those assumptions into mathematics, it's actually going to turn out to be what we really need in order to correct actively for drift. So now that I have already set up some at least conceptual framework of what are the key players, the key ingredients, the key components that we need to introduce in our models, I'm going to specialize exclusively on a situation that we want to use this framework to correct for drift. And I'm going to simplify it, as you can suspect. I'm going to introduce specialized simplifications that apply only for drift correction. And one very important simplification that we can do is basically if we accept that the error that we accumulate are in some sense proportional to the time that is happening, that is occurring, then it is relatively safe to assume that the errors, the displacements that are happening while the probe is moving from pixel to pixel, it's going to be much, much, much smaller than the displacement that is going to be accumulated when the probe is moving from one frame to the other, simply because the time scales are vastly, vastly different. So if we think that, then in reality, we really need to think about errors that are specific to each frame. And that's why I'm going to simplify my formulation. I will assume that each frame, frame 1, frame 2, frame 3, are associated with pretty much the same value of error. Again, I emphasize it's a simplification, but if we want to come up with a method that can be deployed on real time, unfortunately, we need to do some simplifications. And this one is a very valid one. Now, if we assume that the error that is happening is the same, is uniform throughout a frame, then we can simplify also the corrections, because in each frame we want to compute just one correction. And if we consider just one error per frame and one correction per frame, obviously we can stop thinking, or at least momentarily, we can stop thinking about pixel values as individual pixels, and we can start think of them as entire frames or entire fields of view. What is the advantage? Because if I start thinking about the entire field of view, I can actually do something smart at this point. I can take two successive measurements, two successive frames, and I can use my favorite image registration method. I don't want to register these two images, but I want to use the same methodology that I would use even if I had to register the two images to basically come up with an optimal displacement that occurred from one image to the other. And these are going to be my omega variables, which I will call pseudo-observations, because they are not directly coming out of the microscope. They require a little bit of processing. So what is my omega 1? Basically, I will compute the omega 1 by trying to find out what is the best way to translate one frame, my second frame, relative to the first frame. Now, why these why these pseudo observations, the omega variables, are important? Because now I can start building my model, a more quantitative model than what we had before. So let's think a little bit of what those omegas may actually represent. So the omega variable is, as I mentioned already, the optimal translation that we need to apply in one field of view to match the subsequent field of view. So in some sense, if we take the actual position of any pixel in our field of view at one frame, and we add the corresponding quantity, the corresponding omega that we just computed, this would be pretty much the same as the actual position of the same pixel on each subsequent frame. And I'm not using here equality, I'm just saying approximately, because unfortunately the omega variables are computed based on registration methods which operate on the frames, and the frames are already contaminated with noise, electron noise, and some of this noise is expected to be propagating down to the omegas. So omegas are just, let's say, approximately optimal displacements. So in any case, we have something quantitative here and we can keep building on it. So what our framework tells us that its actual position is basically the sum of three things. The target position, this is my RP, which is the same in both sides of this approximation. The drift that occurred in the two different frames, minus the corrections that I have applied while I was acquiring those frames. So now I can manipulate a little bit. I can rearrange terms here. It's not very difficult. You can immediately see that what my omegas actually probe, actually target, actually track throughout the experiment is basically the difference on the error displacement that is accumulated between successive images, plus the difference of the corrections that I have applied. So I'm going to make that a little bit. I'm going to build on that. I'm going to take advantage of this approximation, and I will make it a little bit more rigorous. So In this case, if we want to simplify our formulation, I'm going to gather the difference in the displacement that is happening between successive frames into just one variable. This is my f variable. And whatever error that I'm doing in the approximation, I will just gather it in some noise. So basically, if we read literally the last equation, what it really says is that the pseudo measurements that we obtain, it's basically the sum of some f, which I will call drift velocity, because in reality, that's exactly what it is, plus or minus the corrections. So if we depict them on our schematic here, these are going to be our f variables. Each pseudo observation is going to be associated with an f variable. And basically how those f variables depend is basically on its nearest drift errors. Okay. Currently, we have all the key players. I have introduced everything that we need. I have introduced all the formalism. Let's try to simplify and let's try to throw out things that we actually don't need anymore. And because the omegas are computed directly from the frames, at this stage, we don't care about how the frames are corrected. So I'm going to throw away the variables that we don't need anymore, and I'm going to keep just the pseudo observations, the corrections, the drift, and the Fs. Now, another simplification that we can do here is that, actually, before we do another simplification, let's try to read our last equation carefully. It says that our omega is basically the sum of the f variables and the corresponding corrections. So literally, the last equation corresponds to the new arrows that I have just introduced. This is super interesting at this point because we can see that the omegas respond to the f variables and they are only indirectly connected to the drift that contaminates each particular frame. So what I'm going to do, I will simplify even further. And instead of having the displacements there, I'm going to remove the displacements entirely. And what I'm going to do, I will prescribe, or I will try to model, I will try to prescribe mathematically and statistically directly the evolution of the drift velocity, which turns out to be exactly what I need and sufficient for the purposes that I need. So if we get rid of the drift velocities, if we get rid of the drift displacement and we focus only on the variables that actually affect the pseudo observations, then we end up having only this arrow that tell us how the drift velocity changes across frames. So basically what I'm trying to do here is that I'm repeating the same procedure that we typically say. If we want to model the motion of, let's say, a material particle, we can actually prescribe the velocity and follow it, or we can actually prescribe the acceleration. Through the acceleration, obtain the velocity, and through the velocity, obtain the position. So here we are going with the latter. We are somehow we need to start thinking about acceleration type of variables. So we have all the key elements that we need. Let's try to think a little bit bigger. In a real-life experiment, we are going to acquire very many frames. And now what you see in front of you is the corresponding formulation that we need to use when we try to model more than one frames. As you can see, we have the frames. These are the raw data in this line. Those can be used pairwise to compute pseudo observations. These are our omegas. We need to use image registration techniques to do that. And we need to be careful what sort of image registration technique we need to use. So it is computationally fast. Most likely we want to use some registration technique that relies on the Fourier, that does computations in the Fourier domain. Up here we have the corrections that we need to instruct the instrument every time to use. And on top, we have the dynamics. And on top, we have the evolution, the time series of successive changes in the drift velocity that, unfortunately, we need to make a very clear assumption. We need a model for those arrows. And I haven't really told you what this model should be. That's what I'm going to do in the next slide. But before we talk about how we can actually model the evolution, how we can represent those vertical arrows mathematically, I'm going to basically assume that this is already done and just give you an illustration of how we can use the framework we have just developed in a real-time setting. So let's say we have a working model which is not complete. I haven't finished the description of the model yet, but let's say we have it, and let's say we want to run an experiment that will actively correct for drift. So, in the very beginning, before the experiment begins, this is all that we have. There is no variable that is shaded. This means we have nothing that we have acquired yet. Before we acquire the first frame, we need to decide on the first correction. So unfortunately, at this stage, the only thing that we can do is a passive choice. So basically, decide on what is the correction on the first frame completely at random, completely independently of any measurements. Now, I believe at this stage, all of you will agree the best choice is apply no correction, which corresponds to alpha equals 0. And this is perfectly fine. So we make a choice for the first correction. We use it to acquire the first frame. However, again, with just one frame, we cannot really do much because with one frame, we cannot compute the corresponding omega. So the second correction that we need to do, unfortunately, we still need to do a passive choice. So let's say we try to collect the second frame also without applying any correction. So alpha equals 0. Now, once we have made the second choice, we acquire the second frame, and once we acquire the second frame, we can compute the first omega. Because we have two frames, we register them with each other, we can get an estimate of what is the displacement happening between them. Once we have the first omega, the first pseudo-observation, then we can make a good estimate, about what should be our first F1 variable. And if we can make an estimate of our first F1 variable, then we can use our model to make a prediction for what should be our second F variable. Now, once we make a prediction for F2, we can actually use it to decide on what should be the optimal correction that we need to apply in the third frame. So, before we acquire the third frame, we can actually use our model, and at this case, we can make an active decision. Active because this decision is informed by the data. The model can actually start responding to the frames that we have collected. Of course, the first active decision is not going to be a pretty good one because we have just one data point informing our model, so we don't expect to be very accurate. But this is perfectly fine because a bad estimate is actually much better than no estimate at all. So we make the first active decision, we acquire the third frame, we have the third frame, we can now acquire a second pseudo-observation, and now with two, omega 1 and omega 2, we should be able to get a much better estimate for F2, which we can use it to make a much better prediction for F3, and using the prediction for F3, we should be able to make a decision for alpha 4 that is much more accurate. Once we do that, we collect new frames, new pseudo-observations, and we keep on. And as you can see, every time I acquire a frame, my dataset increases, so the estimates, the quality of my estimate should be much better, so subsequent corrections should be actually much better. And that's how actually we want to deploy a methodology to do active correction during a real-life experiment. So now I'm going to, so far, what I haven't really told you is basically the most critical ingredient, how we can actually model the evolution of the variables that we need to make predictions. So let's take a closer look. Let's try to see what is the minimal formulation that we need to create in order to be able to come up with a model that allows to make active predictions, that allows us to make predictions of the drift velocities. And the minimal, and possibly the minimal formalism that we need is what I'm showing here. It requires at least, it requires exactly two equations. So what I'm having in the first equation is basically, I'm going to assume that the drift is just the drift acceleration from one frame to the other is basically just a constant multiple of itself. So it's either always increasing or always decreasing. That might be perturbed by these zeta variables, which are going to be some sort of random variables that we're going to model the stochasticity in the dynamics. The second equation that we need, which is going to model the vertical arrows, basically how the F's are linked with the omegas, is the equation that we have actually already seen. This is going to be, each omega is going to be the corresponding change in the drift displacement, the corresponding drift velocity, plus or minus the corrections that we have already applied. And in order to account for error that might have been propagated from registration, I'm going to introduce those random variables etas. So what we have here is actually a very nice, very robust mathematical model. This mathematical model consists of two types of variables. We have hidden states, these are our f's, and we have also noisy observations, these are our omegas. And in order to account for either random dynamics, random perturbations throughout time, we need to introduce random variables, the zetas, which are going to have their own variants. And also in order to account for noise on the measurement side, we are going to model the eta as normal random variables with their own variants. So what we have here is a statistical formulation that we can use to make our predictions. And it turns out that our model is a very special case of a much larger family of models, what we call linear Gaussian state space models. Why these are called linear? Because all the relationships in our model are linear relationships, just multiplications and additions. All the random variables in the model, they are Gaussian random variables, our statistics are normal. And of course, it is a state space model because we have state variables. Now, what makes our model very, very special, of course, is that our model contains parameters, and they are very critical parameters. One is the G parameter, which tells us what is the multiple of what is the gain factor on the acceleration, and what are the variances of the dynamics and the noises. So in order to use our model, we need actually to learn those parameters. We need to adapt the values of those parameters on our data. And we can actually do that because if we follow the theory of linear Gaussian state space model, we have very efficient formulations that can give us two critical factors. One is the likelihood, which is basically a measure of the fitness of potential values for the parameters relative to the data we have seen, which we can use to find the optimal values for the parameters. And the other one is the predictor. The predictor of what? The predictor of the next measurement given past measurements. And why this is important? Because we can use the predictor in order to decide on the optimal corrections that we can actually apply during the experiment. Now, those quantities, we can actually compute them very, very efficiently. The methodology that we need to follow is basically the same algorithms that we apply when we do Kalman filtering. I'm not going to give you the formulations of Kalman filtering. The details are available out there. It's just a combination of linear algebra, how we efficiently do matrix vector multiplications in the best possible way to obtain the two components that we need. Now, you may wonder why we call it Kalman filter, because the algorithm was initially developed by Kalman, and the main task of the Kalman filtering algorithm was to compute filters, which if you really want to find out all details about Kalman filters are the estimates of a state given measurements up to itself. Now, in our case, we want to use the computations of the Kalman filter, not to compute the filter itself, but to compute byproducts of the Kalman filter, which is the likelihood and basically the predictions of the measurements. Now, before I show you some demonstration of how this method is working, I just want to highlight very quickly how the computations will go through a real-life situation. So let's say we are running our experiment. We have already acquired capital N measurements, capital N different frames, and we are about to begin the acquisition of the next frame capital N plus 1. So at this stage, let's say we have already computed past corrections. So our previous alphas have been computed, so we can run the next measurement. And we have also computed pseudo observations, omegas, up to the previous frame. So given that we already know the correction that we need to apply at this frame, we are going to use it to acquire the next frame. And once we acquire the next frame, we need to prepare for the next frame, which means we need to compute corrections for the next frame. So how this will typically go, we are going to use the measurements that we currently have to optimize the likelihood. This really means we need to adapt the parameters of our model. We need to do a learning procedure, which is actually quite fast. to decide on the optimal parameters of our model. And once we have optimal parameters, then we can use our model again under the optimal parameters to decide on what should be the next correction that we need to apply, so it minimizes the predictions of the next measurement. And that's how we can compute the next corrections and keep going. So at least conceptually, these are the steps, the main steps in the implementation of an algorithm for active drift correction. Now, before I stop and take your question, I just want to give you an illustration here. This is the same example that I showed in the very beginning, where we have this pronounced drift. And in order to make it a little bit more quantitative, in the bottom panel, I'm showing a time trace and time series of the corresponding frame differences. So basically, every time you see a stem on the bottom panel, this is basically the Frobenius norms of the corresponding frames. What is the Frobenius norm? It's just a metric that tells me how different the two images are. When this is very large, it means that my frames have drifted considerably relative to each other. When the value drops, this means that my frames are almost identical. And what we currently see is a situation where no correction has been applied. This is, let's say, how we typically run an experiment without worrying or without applying any active corrections. Now, what we see here is what is going to happen in a situation where we image exactly the same specimen, under exactly the same drift, but in this case, we apply corrections actively. So basically, we develop the model that I described, and we use it to actively decide on the corrections. As you can see, drift is at least visually completely absent. Our microscope has stabilized. And there are also some nice features that we can look in the time trace right here. Remember that the first two corrections need to be decided passively, which means the first two frames are decided, are basically uncorrected. As you can see, the difference between the two frames is actually quite high. That makes sense. However, the third frame in the experiment is acquired under a correction. Because it is acquired under a correction, as you can see, the second stem, the second difference is actually much lower. However, with just 3 frames, we have just one observation to use in the model, so our parameters are not learned very accurately, and that's why we have significant error. However, as we keep going, we accumulate more data, we specify the parameters, we learn the parameters much more carefully, and subsequent corrections are actually much more specific. And this is pretty much a demonstration of how this algorithm can work in practice. Before I take your questions, I just want to highlight that if you like the methods that I'm describing here, and you want to find out more about the computational algorithm of the implementation of Kalman filters or different dynamical models that we can use in similar applications, we have a textbook, an entire textbook that we can actually find and take a closer look in all details that I didn't have the time to cover today. So at this stage, I'm going to finish, and I would be happy to answer any questions that you may have.
Thank you, Ioannis. So are there some questions here? Okay.
So on the last feature, so this is not an MCMC.
So the question is, what is the computational implementation that we are having, if it is a full MCMC method or not? The answer is no, this is not MCMC.
So there is no.
No.
Okay. We have something in the chat. Do we have somebody? Some questions from the chat here? Is it easier? Oh, there is somebody.
Yeah.
Sorry, you go.
Thank you for your fantastic presentation. Actually, I have a question about the result. As we can see, the result is fantastic and you know dynamically in the frame. My first question is this method it's robust, for example, we can apply in any kind of microscope, you know, outputs. And the second question You know, we have two domains. One of the time series domain, one of them it's a location domain. Imagine we have a lot of nodes, which is the photons of this stuff in the images, and we have the time series, which is difference between each frame. Did you study the effect of both of them, location versus time separately, to understand which one is dominance, or somehow why it's actually the root of this problem, not just solve a problem. This is like, I don't know, I can't explain clearly the problem.
Yes, let me repeat the question for the audience. So there are two questions here. The second question is whether there is a correlation between time and space. I think the correct way to put this question is whether we are correcting for drift or for distortion. So as long as you want to correct just for rigid motion from frame to frame, what we are doing here is nearly optimal. However, once we start thinking about different corrections that need to be applied at different pixels within the same frame, then we should be thinking about distortion, correcting distortions. And as I mentioned in the beginning, this is a very different problem, simply because we need to apply completely different methods to correct the signals that the instrument needs to respond. The problem here is that we typically need to follow reconstruction procedures, which are very expensive. So it's extremely difficult to imagine a distortion correction method that can be employed while the microscope is working. And there are two reasons for that. One is reconstruction is expensive by itself. Second, we need to be thinking about methods that can give you results while the microscope is moving from one pixel to the other, which is extremely, extremely low by itself. So the second question is mostly a different type of problem than what I've been focusing on today. Now, what was the first question? I forgot it.
Application to microscope?
Yes, perfect. So the first question is whether this methodology of active correcting for drift is transferable between different microscopes or different modalities. The answer is actually yes. The model is pretty agnostic to the source of the data. However, there are some caveats here, which I haven't really talked about. And those caveats, they have to do with the quality of the pseudo observations, how you can actually take a proxy signal that will tell you something about the state of the microscope currently. For drift correction, we are using image registration to compute optimal displacements. Now, in order for image registration to give you reliable estimates of the displacement, you need, first of all, to have images that are relatively clean. So a fundamental assumption here is that we are going to have relatively low electron noise. And second, that we don't have edge effects. Edge effects are minimal, which means that our images actually need to be relatively large. Now, if you want to come up with your own experiment or your own microscope that fundamentally is giving very noisy images or very small fields of view, then most likely the methods that I described today need to be adapted heavily. Does this?
Yes, thank you. So
Perfect.
I had a quick question. It doesn't really make a difference for your method in which path we are running through the image, right?
So yes, this is absolutely correct. The method is agnostic to the trajectory that you follow. And actually, we don't even need to know, because the actual position of the probe on the left and on the right side, they disappear. So as long as you follow the same trajectory within a frame, this method should be applied. Now, if you want to change the trajectory from frame to frame, the method needs to be modified. We can modify it. It's a relatively easy modification, but a modification is needed.
Okay, very good. Well, yeah, okay. I think there's a big potential here because we want to place the beam, of course, at random position when we do our analysis. So we need to know where the sample is at that time, right? So that's where he comes in. Just because we did that in yesterday, place the beam somewhere, and we learned how to do that in machine learning. Of course, we want to hit the location exactly independent of drift. Right? So that's where the drift.
To piggyback off of that, it's really interesting because I want to hold samples still as possible so that I can, maybe blast a certain spot or something. Then that changes the image. So how would you take that into account in the method that the image might be changing frame to frame, even if just locally or something?
That is another very important question, very interesting question. To repeat it for the audience online, the question is what would happen if the specimen changes across frames, either because we have degradation or because we actually manipulate the specimen to change. The short answer is, as long as the changes are pretty localized to a small number of pixels in the entire field of view, the method could be applied. However, if you are thinking of more extensive modifications that cover a significant part of the entire field of view, then the methods need to be modified. And how much? It's very specific to the type of manipulation you want to do. If it is simple degradation that is affecting pretty much all locations the same, okay, possibly we can live with the current method. But if the modifications are very localized, then we need to account for those modifications somehow in the method. Does this answer the question?
Yeah, it would be very localized. So would be single atom going away. So, yeah. Okay. Cool. Thank you. Thank you again.